Who has questions next for Todd? I guess that would be the...
I still had some comments and questions.
Go ahead, David. I'm sorry.
Oh, that's fine. So I just wanted to say that the scalar field that is going in that Lorentz gauge thing, I know exactly what's going on, and this is kind of a controversial topic. And the main reason why academia doesn't accept this is because it pokes a hole to the entire idea of gauge invariance, which is an important foundational concept for everything that's going on here. But I don't think the solution is to say that we should throw away gauge invariance, which, like, I've done some work on this and I haven't published on it because it's very subtle and it takes a while to figure out. But the metric affine gravity theory is the gravitational theory that gauges how you have rulers and metrics and length and stuff. So, so I heard some comments before and people say, oh, well, that's not, maybe gravity actually is this. That is exactly what this metric affine gravity framework is. And within that, you can reconcile some ideas such as Tesla or others back in the day who would have preferred variable speed of light models rather than curvature. And that might be an interesting perspective to take. But in terms of convincing academia, a lot of work is needed done to go into the complicated math and then make it simpler to see if we can get back to these simple ideas that are kind of being talked about, which is kind of why I think a lot of the heaviside gravity people like it because it's so simple. But so, I think you're on the right track, Todd, in terms of focusing on that potential. But then at the same time, I wouldn't just stop and say, well, like, we fully understand gravity from that perspective. So I think in time, there can be this story that will come out where the way we think about gravity kind of unifies the ideas of Tesla and Einstein in a more friendly way, because Tesla was his whole point was saying, like, space-time is not a thing. It doesn't have properties, right? It's like we're measuring these events, but there's nothing there. The space-time, he's saying there's this ether, this material, and really that's what all of the stuff that I was talking about before is getting back to. So it actually is in that gravitational framework of general relativity, if you refer to it as the most general theory of relativity, because that's what it is. But it's just taking time for quantum gravity people to realize that. And so once all of that occurs, there should be simplified theories that come out that might be helpful. So yeah, as you're doing this research, don't feel like you're completely alone, or don't think you're as radical as you might think you are, because there is a chance that, conventional academia could reconcile all of this.
I appreciate that. I just wanted to say that I've been working on this for over 30 years. And so I'm 59 and a half, and I've been doing this for a long time, since I started dreaming about this when I read my first book on Einstein when I was 17. So it's been a long time coming. And I've tried to get published. I've had several papers published a bunch of them in an old journal called Physics Essays, because that was the only place that would publish me, because I'm not associated with any research organization, or, I've got a Bachelor of Science from UC San Diego, but I'm not affiliated with them, so they won't publish my work. So I decided to bypass all that and go straight to, what do I need to make it work? And then once I have something that works, then maybe people will notice. But so that's where I'm at. One thing I'd like to mention, though, Jack wouldn't let me finish, because his cosine theta idea is wrong, and I can explain why. And the reason it's wrong is, like, in my model, and as I was saying, gravity is a loss of power. So time dilation and length contraction the matter itself is losing power because it's not being excited for those energy levels anymore. And so it collapses in on itself and free falls. Antigravity is the opposite. You're exciting the matter. And exciting the matter, you're doing work on it, just like lifting it to go uphill, lifting it up. You're doing work on the matter, which inflates it. Energy, the matter gets excited, it inflates in size. As the matter volume increases, the energy goes up slower So the energy density is going down as it inflates. So as like I lift this battery up, its energy density went down. And that's the nature of negative energy density in warp drive and in this equation, is that in a variable speed of light model, the speed of light here is slower than the speed of light here. Same thing. It's the same procedure. It's the same process. And so you don't need a negative energy density that's below zero. You need a negative energy density added to the positive energy density of matter, which makes it less dense.
It's all about how you calibrate everything you're working with. So it could be possible that different calibrations actually are agreeing in complicated ways. So, that's why I like to stick to general relativity, just because there's so much and stuff beyond that, just because there's so much experimental success. I mean, cosmology is a mess too, but that is being figured out with conformal gravity. And so, I mean, in terms of other theories of gravity, like, I'm not trying to shut them down or anything like that, but if you're going to use intuition from that, then we need to first make sure that theory is, comparably successful to, can we get the perihelion of Mercury? Can we get all these different things? So, just comments.
But if I could jump in, David, I really like that, when you just expressed the framework of using a model, right? And I mean, Todd may be using a slightly different model. I've heard, because I've done a lot of interviews in this area, I've heard probably hundreds of different models. But I think it's always important to remember that we are working within these frameworks, right? Now, whether that's custom built or like David is working within general relativity, or there's QM, and each of these models has limitations, and, they've got their own structure to them, And so I think that's one of the things that I've seen is a lot of people run into trouble because they're kind of like, well, this is how it is, this is how it isn't. But then that always kind of relates to the model that you're working with too, right? So.
I just want to say that back in the late 1990s, Hal Puthoff and I both developed a concurrent model based on, we called it the polarizable vacuum model. He called it the polarizable vacuum representation of general relativity. And in that original paper, he showed how it agrees with the perihelion of Mercury and time dilation and all the experiments of general relativity that rely on basically the Schwarzschild solution. And I came up with a similar theory. And then I took it one step further because I took it down into quantum mechanics and damping and QED, and showed that when you add a relative damping factor to the equations of QED, you get the polarizable vacuum model exactly. And it's already been shown to match general relativity in all the observable experiments. And we did this back in the late 90s and early 2000s. And Jack now, puts a refractive index in Einstein's equations and, claims he thought of it. But Hal and I were doing this with the refractive index since 1998. And we had the polarization and the magnetization in the TUV tensor, decades ago. And I wrote a paper in 2003 on warp drive, propulsion, and Maxwell's equations. And on that paper, I, hypothesized that the effect you want lies in the hull of the ship, not in the space around it. And so all of this stuff has been around, basically about 18 years ahead of where Jack is on this. And I know what's going on. And Tim, in regards to what you just said, I agree. Everybody's got a slightly different model, but at times when people are presenting their model, I can see where the differences are and I can tell which one is right and which one is wrong. And sometimes I know it well enough that I can tell you that. And
Well, yeah. And I won't disagree with that. Although the thing that I do like about models is that I think it helps prevent fistfights, right? So that's always a bright spot. You know, it's much easier to agree to disagree. I think that way. You know. So, and I am not disagreeing with what you're saying.
I'm a board educator, so like I like to teach people what's, you know, so and unfortunately I like to correct errors and fix things, and a lot of people don't appreciate it. But I appreciate that David does and Eric did, and I know you guys do. So I'm I'm happy to be working on this stuff, and I'm happy to be part of this group.
Yeah, well, and thank you for presenting. So if it's okay, let's jump over to Mark next. Todd, if you're all set.
Yeah, I'm done.
Okay, thank you, sir.
Thank you, Todd.
Thank you again.